For problem 6.6, I started by looking at the block diagram and identifying the system consistent with two elements arranged in parallel. One path is an integrator with a transfer function of k1 over s, and the other path is a first order system with a transfer function of k2 over ds plus 1. Since both elements receive the same input and their outputs are summed, I knew that the overall transfer function would be the sum of two individual transfer functions. So I wrote the total transfer function as you can see below. And then as after that, I combine the two terms in a single rotational expression by finding a common denominator. The common denominator is sts plus 1. So I rewrote the numerator as k1, ts plus 1 plus k2s. When I expanded and simplified, I got k1 plus k2 s plus k1 in the numerator, and the denominator stayed the same. Next, I identified the poles by setting the denominator equal to 0. That gave me one pole at s equals 0, and the integrator and another one at s equals negative 1 over t from the first order term. And I found the 0 by setting the numerator equal to 0, which gave s equals negative k1 over k1t plus k2. I analyzed the sign of that expression to determine when the 0 would lie in the right half plane. That happens when the numerator and denominator are on opposite sides. A pole at 0 contributes integrating behavior, while the pole at negative 1 contributes an exponential decay term of the form. And then for problem 6.7, I started by interpreting the given block diagram and recognizing that the system consists of two dynamic paths contributing to the pressure response. One path behaves like a second order system, and the other behaves like a first order system. The problem involved using step response information to determine the model parameters. First, I expressed the input change as a step function. The pressure input changed from 4 to 6, so the step magnitude was 2. In the class form, that becomes 2 over s. I then multiply this input by the transfer function of the first order path, which was negative 3 over 20s plus 1. Multiplying these together gave negative 6 over s but 20s plus 1. Then I performed an inverse Laplace transformation, recognizing this as the standard form of a first order step response. That gave the time domain expression as qt negative 6, 1 minus negative e negative t over t. Next, I determine the steady state gain of the overall process using the definition of process gain as the ratio of the steady state change in output to the change in input. From the graph, the pressure increased from approximately 12 to 27 to the output change was 15. The input change was 2, so I calculated the gain as 15 divided by 2, which equals 7.5. That gave the overall steady state gain of the system throughout the system. I relied on the recognizing of standard Laplace form. However, that was kind of confusing, and using the steady state relationship to exact the system parameters.